In this video, we will answer a few practice questions, actually just three of them, including what's shown here. They're basically word problems on approximation. So, uh, something that you have to know is that one of the applications of total differentials is approximation given multiple variables. So, provided that we have m is equal to f of xyz, um, basing on the formula on total differentials. So dm is equal to partial m over partial x, the first variable, times dx. And then for y, partial m over partial y times dy. And then partial m over partial z times dz, z as the third variable. So this is how the typical formula would look like. Wherein, previously, whenever we solve for example, we have this kind of scenario, we just look for these three. And essentially, dx, dy, and zz are just copied as is. But in the context of approximation, these variables actually have a value. And these are usually the errors. So dx is the difference or error in x, dz, difference or error in z, dy, difference or error in y. So yeah. And dm, on the other hand, is now with a more specific definition in the context of word problems. So it is the difference or error in capital M. So yeah. Let's move immediately to the first practice question in order to apply what has been mentioned. So we have this word problem might look familiar to you. It's actually the same word problem that we used previously. I can't really remember specifically what method we used, but another method of solving this same practice question is through total differentials. So, what the? Our figure is not exactly a cube. It's almost a cube. It just so happens that the height is different from the width and length. So we have LWH, length, width, and height. And note that these are all in the unit centimeter. It was identified that these dimensions were 2 millimeters longer in all dimensions when measuring the box. So 2 millimeters longer. So when you add 2 millimeters in each of these measurements, that makes the actual measure of the box. So approximate the box volume and identify what is the percent error of the volume when compared to its supposed dimensions. So how do we apply total differentials in solving this kind of problem? So let's see. We'll be solving this question using two methods. We'll be comparing solving through DMV or differentials with multiple variables. Or, the other method is going to be using partial derivatives. So, total differentials basically. I'll just move this to another. So, I kid you not, the other two questions will be harder. So, essentially, this practice question is just going to reinforce the basics, so it's easier to understand the next questions. So again, we are given 2 millimeters as the longer, in a way it's considered the increment, so it's technically also called the error. So in all dimensions, meaning that means dB, or length, since length and width are the same, let's just call them the base measurement. So the increment in the B is 2 millimeters, And the increment in the height is also 2 millimeters. So let's solve first using the DMV method. So method 1. Without expressing h as a function of the base, so the formula for the volume of the figure is b squared times height, right? And using DMV, so dv is equal to 2b times, so we're gonna apply product rule. Both of them are not going to be considered constants. All of them are variables, so nothing is going to be zero as far as I can tell. So h is going to be, just write it, plus b squared, just write it, and then, oh yeah, don't forget. After finding the derivative of b squared, so we write 2b, right? There is something called db. I hope you can visualize it. So d over dx of b squared is equal to 2b raised to 1 times du over dx. This du over dx is this. We can just rewrite it simply as db. And I tell you, once you kind of get the hang with how we usually solve total differentials, you will understand that this one is the du over dx in what I just wrote. So after that, well, yes, just copy the height, plus b squared times the height is going to be 1, right? And don't forget dh. It is easier to understand that that's how you solve it, because db and dh are the ones here. Those are the given values. Eventually, we will substitute the values. So that's what we're going to do. Base is equal to 25, right? So 25. By the way, convert these to cm. That's the best method right now. Instead of converting these cm values to millimeters, that's going to lead us to dealing with bigger values, and it's harder to do mental math when we have that kind of situation. Especially, as far as I can tell, you're not allowed to use a calculator in the test, so everything is mental math. 2 millimeters is 0.2 cm. Dm, cm, mm. Cm to mm is just 1 decimal point away, so yeah, 0.2 cm. db is 0.2. Height is 32, plus b squared times dh is 0.2. So essentially, all of these values will, hang on. Okay, we're good so far. We can simplify. Let's try to turn 0.2 as 1 over 5. 25 times 25 times 1 over 5. 10, 320. So you cancel, right? 10 times 32 is 320. Plus 5. 5 times 25 is 125. 125 plus 320 for 445. cm, since this is volume, it's cube. So this is the dv. Approximated box volume, I believe. Now, let's try to find the same value, this time using partial derivatives or total differentials. So dv is equal to, what variables do we have? Base and height, right? So the partial v over partial, let's say, base times db, plus partial v over partial height. The other variable is the height, times dh. So let's first identify what partial v over partial b is. In that case, we are going to render the height as constant. What's our reference? The volume of the shape. Again, it is b squared times h, right? So put the h at the left side, and then derivative of b squared is going to be 2b. Don't be confused. In total differentials, you don't write dB afterwards. That's not the case. You will do that later, but just not here. So the answer is going to be 2BH. How about partial V over partial H? So B is going to be considered a constant. So B squared, and then derivative of the height is 1. So the answer is B squared. Note those values. This time, we substitute. So dV is equal to 2BH times dB plus B squared times dH. Okay. Base is 25, right? And the height is 32. dB is equal to dH, which is 0.2, or just 1 over 5. 25 times 25 times 1 over 5. Let's try to cancel. So we can simplify. 5, 320. So right now it looks familiar, right? 25 times 5 is 125. So we get essentially the same thing, 445 cm cube for the approximated box volume. We got the same thing. Regardless, both are different methods. One is through DMV, the other is through TD. But yes, we got the same thing. Now, we are tasked to find the percent error volume when compared to its supposed dimensions. So how do you find that? Percent error. So in the context of volume, the formula is this: dV over V1 times 100%. So the V1 here refers to, since we have 25 for the base values and 32 for the height, right? And again, reading the problem, it was found that the dimensions were supposed to be 2 millimeters longer so that the volume would be correct. So we can say that V1 is the previous volume, or the volume that isn't correct. So yeah, the approximated box volume divided by it times 100 is the percent error. So dV is 445, right? And V1, so 25 times 25 times 32, coming from the formula B squared times height, and then times 100. How can we simplify this? Eight. 445, 10 times 45? No. 589. That's a weird value. 25 times 8. 89 times 540, 45, 445. How can we make 89 a smaller value? 2? Nope. 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 589 over 40. 2 9 over 40. 2 point, let's say 9 is 10. 1 over 4. 2.25 approximately. Yeah. So that is an approximation of our percent error. So this is the answer. Actually, according to the answer key, the more precise value is 2.225%. But nevertheless, it's still pretty close. So that's it. That's how we use total differentials to approximate given multiple variables. Those multiple variables in this context are height and base. Next question. So electrical power is given by P is equal to V squared over R, where V is the voltage and R is resistance. The corresponding units are shown at the top. Approximate maximum percent error in calculating the power if 120 volts is applied to a 2000 ohm resistor, and also the possible percent errors in measuring V and R are 3% and 4% respectively. So how do we start given this kind of question? So let's start first with what we are provided. Just to clarify what these values correspond to, they are not the same as the error value as earlier, the DH and DB. In this context, they are percent errors. Okay, so let's write them down. Percent error for the volume is 3%. The percent error for the resistance is 4%. In percent error, again, the formula is dV over V1 times 100%, right? So that's going to equal to 3. And apparently, we have V1 as 120 volts. 2000 ohms is gonna be our R1. Okay, so dV over 120 times 100 is equal to 3. dV times 5 is equal to 18. dV is equal to 18 over 5. 5 and 15. 3 over 5. 3.6. So that is our dV. For, oh yes, sorry. Not to confuse you, earlier, the percent error for the volume is the capital V, right? But since we're dealing with volts, we just write small v. Okay? My bad. So, that's it. We were able to find what dV is. How about for dr? So, the formula that we start with is this, right? And so dr over R1 is 2000 ohms. We will cancel. So dr is equal to 4 times 20. That's 80. Don't forget the units. So, what else? So, using total differentials, how do we form our equation? So, again, our P is power, right? So dP is equal to partial P over partial V times dV plus partial P over partial, what's the other one? Resistance. So partial R times dR. Do we know the value of dV? Yes, we do. Actually, yeah, that's what we solved for. These two are these two respectively. So at this point, what we have to look for are partial P over partial V and partial P over partial R. So partial P over partial V. In that case, we will render R as constant. Where is the formula? P is equal to V squared over R. Okay? R is a constant, so set it aside. So 2V. 2V over R. That's it. Other one, V is going to be the constant. So we'll apply quotient rule. R times 2V minus V squared times... Oh, wait. This is supposed to be 0. Derivative of R is 1 over R squared. Negative V squared over R squared. Okay, that's it. So I believe we can start substituting the values already. So dP is equal to partial P over partial V, that is 2V over R, times dV, which is 3.6 volts, right? And then plus, or let's say minus, V squared over R squared times 80 ohms. Then we'll substitute the values. What is our volt again? 120, right? And R is 2000. Substitute further. 2 times 120 over 2000. 3.6 can be rewritten as 18 over 5, right? This one. And then V squared, V is 120, square it, over 2000 raised to 2 times 80. Okay, so yeah, let's try to simplify this. One thousand to 24. 6 times 4 times 6 times 3 over 10 times 10 times 10 minus 12 times 10 times 12 times 10 times 8 times 10 over, oh, this is crazy, 20 times, what makes 2000? 20 times 100. Okay, let's try to cancel. There's a lot to cancel. How do I want to start this? 3, 5. Let's bring this here below. Let's further simplify. 3 times 2, 6. 6 times 3, 18. times 3 over 125. Cancel, cancel, cancel. Cancel, cancel. This becomes 10. 5, 4, 5. That's it. 12 times 12 over 20 times 25. $54 over 125 minus, what's 20 times 25? 500. Wow. 125, 250. Oh, we can. Yeah. We can find an LCD easily. 12 times 12, 144. 500 for 54 times 4, 216. 216 minus 144. 2, 11, 7, 72. Are we good? Let's see if I got it right. Looks like we did. Nice. Okay, so we can, this could be the answer already. But if you want, although personally I wouldn't, I convert this to decimal form, so that's going to be 0.144 volts. Why is our unit in volts? I don't get why my answer is in volts. It's supposed to be watts because this is, again, dP, right? So the unit has to be the unit of power, which is watts. Okay. Now, we were able to identify the maximum percent error in calculating the power. Are we? No, I don't think we have yet. But what we were able to find is instrumental in finding out what that value is. The maximum percent error of the power. So that's gonna equal to dP over P1 times 100%. So at this point, I think you can see a pattern. dP over P1 times 100. Always times 100 if percent error is involved. So dP is 72 over 500. I'd place the fraction form instead of the decimal since we're gonna cancel anyways. P1 is what? Is it a provided value? I think it is implied. Looks like, yes. So how do we identify P1? So since this is V1 and that is R1, P is V squared over R, right? So 120 squared over 2000. Let's simplify that. 120 squared. 120 times 120 over 2000. Simplify. Okay. 72 over 500 divided by 6 times 6 over 5. Eliminate the division sign. Reciprocate. We can cancel something. 1, 2. 2. 2 over 100. And don't forget the times 100, okay? So when you cancel, very satisfying, you have an answer of 2%. So yeah, that's it for this question. Whew. Next. So this is gonna be the hardest one yet. My solution paper is an entire page of a long bond paper, US legal. So let's get to it. A chocolate candy is composed of a square prism base and a right square pyramid top. The candy has a side length of 4 cm, prism base has a height of 5 cm, and the pyramidal height is 6 cm. Also, considering the cost of the chocolate itself, it is P2 per cm cube. So we are tasked to approximate the maximum percent error of the candy's cost. If the maximum allowable error for the side is 1 millimeter, for the prism height it's 2 millimeters, the pyramidal height is 3 millimeters, and the cost of chocolate is quarter, 0.25. So we have clearly we do have 4 variables, and the total cost is gonna be the cost times the volume. So again, we have a square prism base and a right square pyramid top. Let's draw that first for better visualization. So that is going to be the right square pyramid top, and the square prism base is this. So this is our H1. That's the prism base's height, which is 5 cm. The pyramidal height is 6 cm. Let's call that H2. Side length of 4 cm, right? So it is suggested that both of these are the same value. Okay. So what is the formula for the prism base? So b squared times height, right? Similar from a while ago, from the first practice question. Only base is abbreviated as S, side. Same thing, essentially. How about the volume of the pyramid? So it's a right square pyramid, so 1/3 S squared times the height. The height here is 2, h sub 2. Not to be confused with h sub 1. H sub 1 belongs to the prism base. So these are the volumes, and the total cost is cost times the volume, right? So what I wrote here were the volumes. Now let's write TC in consideration of those. So we have cost times S squared H1, don't forget this is H1, plus 1/3 cost times S2 H2. Essentially, what I did was just multiply in each of these volume formulas C corresponding to cost. And this time, since we are applying total differentials, we rewrite this as in terms of, well, let me just show you. So dTc is equal to partial Tc over partial C times dC. Again, we have 4 variables, right? So for the side, for the prism height, for the pyramidal height, and for the cost of chocolate, so abbreviated as C. So this is the cost of chocolate. Partial Tc over partial S, that's for the sides of the prism base. Partial dTc over partial H1, the height of the prism base, the height of the pyramidal figure. So this is the one. Now we identify each one specifically. So each of these 4. So partial Tc over partial C, we are going to consider the other 3 variables as constants, S, H1, and H2. Okay? So derivative of C is 1 plus 1/3 S squared H2. Derivative of C is 1. That's it for that. Next. This time partial S. So C, H1, and H2 are all constants. Next. So C and H1 are constants. S squared becomes 2S. That's it. Next, 1/3 C H2, S squared becomes 2S. Simplify, 2S, 2C S H1 plus 2S CH2 over 3. Okay. Next. So with H1, with respect to H1, meaning the rest, C, S, and H2 are constants. So C, S squared are constants. H1, so times 1, plus 1/3 C S squared. So everything is a constant here, so that's gonna be 0. So simply, we have CS squared for partial TC over partial H1. How about partial TC over partial H2 this time? C, S, and H1 are all considered constants. So C, S, H1, this entire thing is going to be 0. Here, C, S, C and S cs squared times 3. Derivative of h2 is just 1. So cs squared over 3. Okay. Do we have dc, ds, dh1, and dh2? Actually, they have been provided already. It's these values. Maximum allowable error for each of the variables. So just to tally, ds is 0. It says 1 millimeters, right? dh1 is 2 millimeters. dh2 is 3 mm. dc is 0.25 per cm cube. So we convert the rest to cm. The cost is 2 pesos. It's supposed to be 2 pesos, not p sub 2. It might be misleading. And then S is equal to 4 cm. H1 is 5 cm. H2 is 6 cm. Based on the figure shown here. Okay, so let us now substitute. It is going to be a very long solution, so I hope you are taking notes, and so I don't have to go back from time to time to what has already been solved. We can just keep writing. So DTC, let me just bring this down. Partial DTC over partial C is this. So bring that here. And then times DC. DC is what? 0.25. Plus partial DTC over partial S. Where is that? It's this. Times DS. DS is 0.1 cm. Plus DTC over DH1. DH1 is this. CS squared. DTC over DH2. So we have this. Okay. S is 4 cm. H1 is 5 cm. S squared times H2 over 3 times 1 over 4 plus 2 times C times S times H1 plus 2 times S times C times H2 over 3 times 0.1. 0.1 can be rewritten as 1 over 10 plus C times S squared over 3 times DH2, which is 0.3 over or 3 over 10. Okay, so further simplify. 16 times 580. 16 times 2, 32 over 4. $80 plus, oh man, 24 times 4, 80, 96. Yeah, 96 over 3 times 1 over 10 plus 16 over 5. 112 over 4 plus 240 316 over 30. Wait. 160, 170, 176. This is crazy. 240 plus 96. 13. 336. And then 16 over 5. Simplify. Common denominator. 15 times 112. Damn. Three, 6 672 plus 12 times 16 192 for 24 15 2544. Woo! Okay. How do we simplify this? I think we can divide everything by, simplify by 4. 15. $636. 15, 30, 45, 60. $42. Essentially, this entire thing is supposed to be 28. This is gonna be 11.2. Wait, we're missing something. Yep, we are missing something. 0.1. Where is 0.2 or DH1? Yeah, C is 2, right? 2 times S squared times DH1 0.2 or 1 over 5. (32 over 5). Uh, 5, 60, 12. 12 times 32. Okay. 2544 plus 384. 16, 13, 9, 2. 2936. (15, 30, 45, 60). 134 out of 15. 15, let's try 7. 505. 8, 40, 120. Okay, 48 point something. That is supposed to be our DTC. But approximately, the answer is 48.8. So, you were able to identify what DTC is. Now, we approximate the maximum percent error of the candy's cost. So how do we do exactly that? So the percent error is equal to the DTC over apparently the total cost, which we don't know what we don't know what the value of TC is just yet. Actually, let's solve for it now. So TC is equal to, based on the formula we wrote earlier, is this. So cost is 2, side is 4, height 1 is 5, plus 1 over 3 times 2 times 4 squared times height 2 is 6. Just simplify. 2 times 16 times 5 plus 160 plus 64 224 is the total cost. So DTC is equal to 48.8, right? And TC is 224 times 100%. Hmm. 112, 50. 25, 5, 6. 488 over 560 times 250. We can rewrite the expression like that. And then, what can we cancel? So 4 times 122 over 56 times 25. Okay, 14 times 4 just to be sure. 56. Okay. 122 times 25 over 14. 2 times 61 over times 25 over 14. 61 times 25 over 7. This could have been 63. 21 point something. 7, 15, 25, 2, 14, 12, 1, 7, 5, 55. Can we recalculate? So we started with 48.8 over 224. By the way, this is just for the manual calculation. If you are allowed to use a calculator, then this is already this already is the answer. You don't have to watch this part anymore. It's just a waste of time. But we are simulating how we will solve the entire problem manually. So it takes a lot of time, I tell you. For 88 over 2,240 times 100. I think this is the right way. You don't make it 1,000, if you get what I mean. 56, 10, 1. That's more like it. I think we are in the right tracks now. 30, 22. 21 point something. 28. 196. 216. Wait. 56. 5 plus 16, 21. Okay. At this point, I think this is already good enough. So we found out that it is 21.8. So that is the percent error value. In the answer key, it is 21.78%, more precise. But I think this should be enough. So that's it. We are done with total differentials. Thanks for watching.